Now, can you hear me clearly? Just raise your hand if you hear me clearly. Okay, sorry. Okay, wait a minute. Yes. Now we have a week 6. Now just tell me once again. Now my voice is clear. Just raise your hand. And this time, okay, it's all right. So today is our week 6, and today we are going to discuss a vector space. So I'm going to upload the PowerPoint slides. Please, wait a minute. So today we are going to discuss a row space and the column space and the null space. So these things we discuss today. So first of all, we will discuss. We have a matrix m cross n. If we have a matrix m cross n, and there are some row vectors are there and some column vectors are there. So these are our, if this is our row 1, this is our row 1 vector, this is row 2, and similarly up to row n. So in Rn means in Rn's dimension. So from the rows of A are called the row vectors. So these are called the row vectors. Similarly, there is a column vector. So for m cross n matrix on the previous slides, the vector C1 and C2 Cn is called the column vectors. So Rn formed from the columns of A are called the column vectors. So null space. So it says that if A is an m cross n matrix, then the subspace of Rn spanned by the row vectors of A is called the row space. Similarly, what is column space? And the subspace of Rm is spanned by the column vectors is called the column space of A. And the solution of a space of the homogeneous system of equation Ax is equal to 0, which is the subspace of Rn, are called the null space. So these are the three definitions of row space, column space, and the null space. So, and the vector x0 is called the particular solution Ax is equal to b. Similarly, the expression is called the general solution. If I write like this, this is called the general solution. And the expression, this is called the general solution, or we can write like this. So there are several theorems are there. It says that elementary row operation do not change the null space of a matrix. So this is a theorem, and once again, there is another theorem. It says that elementary row operations do not change the row space of the matrix. So these are two theorems are there. So now again there is a third theorem. It says that if we have two matrices A and B are the row equivalent matrices, then a given set of column vectors of A is linearly independent if and only if the corresponding column vectors in B are linearly independent. So only when we say that they are equivalent matrices. So similarly, the B it says that in a given set of column vectors of A form a basis for the column space of A if and only if the corresponding column vectors of B form a basis for the column space of B. So this is when they are called the equivalent matrices. So again, there is a theorem. It says that if a matrix R is a row echelon form. So row echelon form, as I told you, row echelon form means whenever we convert the matrix 1, 0, 0, and the rest element will be 1, and the whatever the element will be 1. So this will be 1. So whenever we convert this matrix into like upper triangular, lower triangular matrix, so we say that this is a row echelon form. So it says that if a matrix R is in row echelon form, then the row vectors with the leading ones, yani non-zero row vectors, form a basis for the row space R, and the column vectors with the leading ones of the row vectors form the basis for the column space R. So from this theorem, where we can understand this theorem with the help of examples, we can understand what is the meaning of leading one and what is the column spaces. So with the help of example, we can understand this theorem. So there are several things are there. These are things we read is, for example, we have a matrix is given, we have a the row vectors are there, then we have column vectors are there, and so there are some examples are there. So now these theorems we read early. So now we are going to solve the matrix. We have given a matrix and the basis for row space and column space. So the matrix R is in row echelon form while the vectors are. So we have given a matrix and we will convert this matrix into a row echelon form. For example, we have a matrix R and we have to find the basis. So our first step is we will convert the matrix into row echelon form. So we observe that it is already in a row echelon form. There is no need to change this into row echelon form. So what are the which rows are the non-zero rows? So we observe that we have a row 1 is a non-zero, row 2 is a non-zero, row 3 is a non-zero. So we say that row 1 is a non-zero, row 2 is a non-zero, row 3 is a non-zero. So which one is the first element in the row? So we say that 1, it is the leading one and it is the first element in the row. And here if we are moving from left to right, so in the second row there is a 1, it is the first non-zero element in the row. Similarly, if we are moving from here to here, so we observe that there is a 1, that is a 1, there is a 1 leading element. It's called the leading element. So it is the first element, all are the 0. It is the first element in this row R3. So that we say that the leading element of R1, in R1, the leading element is 1. And similarly in R2, the leading element is 1. And similarly in R3, the leading element is 1. So it is at which places? So in R1, it is on column 1. So we say that it is on column 1. The leading one will be on column 1 dash. In the next page maybe it will show it. Yes. So the vector, so the leading one will be C1. So the column will be, I write column 1 will be like this, and the second leading will be on the column 2. So that's why I write column 2, and the fourth leading will be, and the third leading will be on the fourth column. That's why we write like 0 0 1 0. So this is called the basis for the column space R. This is the way to write a column space. Dear Norman, you say that there have to be 0 in the columns. Say it's a leading one. So I'm repeating once again, dear Norman. I'm saying that the leading one means what leading one. We are, first of all, we convert the matrix into row echelon form. Then whatever the elements, first of all, we consider only the rows which are non-zero. So we consider only 3 rows. These are non-zero rows. We are not considering non-zero rows. We are not. Now we check which one is the first element in the row. So one is the first element in this row. So it is called the leading element. So if we are going from left to right, this one is the first element in the row. So and this is called the leading one in the second row. Similarly, if we are going from third row, so this is the first element in the row, so that is called the leading one. So now these are this leading one in column 1, and this leading one in column 2, and this leading one in column 4. So that's why we say that the C1, C2, C4 are the column spaces. So that's the procedure to write the basis. So let's see some other examples. So it says that basis for row and column spaces are, find the basis for the row and column spaces. So a question is given, A is equal to something is given here, and now we have to find the basis. So as you know, first of all, we will convert this matrix into the row echelon form. So when we apply the elementary row operations, it will convert it into the row echelon form. This is the matrix. It's into the row echelon form. So now, in how many rows we have to consider which have the leading ones? So we say that row 1 have the leading one, row 2 have the leading one, row 3 have the leading one, but in row 4 there is no leading one because of it's all 0. So we say that row 4 no, R4 is not. So there are only 3 rows, row 1, row 2, and row 3. So row 1, the leading element in row 1 at C1 at column 1, and there is and the leading element in row 2 will be at C3 column 3, and the leading element in uh, column 5 will be 1. So these are only column 1, column 3, and column 5. These 3 columns have the leading 1 elements present. So over here in the next slide maybe we will show. So here it is there. So the basis vectors are, so it is written here. So row 1 have the leading one, row 2 have the leading one, row 3 have the leading one. So they write the column vectors of which one. So we see that the column 1 have like this, the column 3 and the column 5 have obtained the leading ones. Now, corresponding to these columns, what are the actual columns are there? So let's see in the previous slides what are the corresponding columns. So this is column 1. So what is the actual column in the main matrix? So in the main matrix there is the actual column will be 1 2 2 1. So I write C1 dash will be is equal to C1. So I write C1 like. So in place of this I write like this, so both of them are same. So similarly, if you go previous slides, what is the in column 3, what we can write in column 3? So we can write in column 3 in the main matrix, in place of C3 dash we can write 499. So I write this 4999. So it is um, it is it is same. So similarly, in the next slides, if we have column 5, so a corresponding to column 5, if you see in the main matrix, there is there is a column that is 589 minus 5. So you can write uh, in C5 dash, in place of C5 dash you can write 589 minus 5. So these are called the bases of the column space A. So hopefully you understand the concepts to find the bases. Is there any question? Okay, okay, so like, so let's we proceed. The next one is, what is the rank and what is the nullity? So as I told you in my face-to-face class, with the help of example we can understand the rank means what is the number of non-zero rows is called the rank. So here with the help of definitions we can understand first of all, then after we will discuss the example. So here fundamental matrix space, we have several things: a row space of A, column space of A, null space of A, and null space of A transpose. So there are several theorems are there. Theorem says that if A is any matrix, then the row space and the column space have the same dimension. Similarly, the common dimension of row space and column space of a matrix is called the rank. It is one example. It is one definition that says that the common dimension of the row space and the column space is called the rank of A, and it is denoted by rank of A. So the dimension of the null space of A is called the nullity of A, and it is denoted by nullity of A. So now we have seen the question. It says that find the rank and nullity of a 4 by 6 matrix. A very big matrix is given, and you have to ask the question, what is the rank and what is the nullity of this matrix? So as usual, in every question we will have to reduce the matrix into the row echelon form. So first of all, we will write the matrix into the row echelon form. That will be is equal to, when we reduce it, that will be is equal to 1, and that second element will be 1, and the third row will be all 0, and the fourth row will be all 0. So what is the rank of this matrix? So as we discuss about the rank, so we have to say that what are the number of non-zero rows are there. So this row is non-zero, and this row is non-zero, and the row third is 0, and the row 4 is 0. So we have only 2 rows which of them are non-zero. So we say that the rank of A is 2. So now we observe that there are 4 equations and 6 variables are there. So we can write x1, we can write in the form of the equation, that is x1 minus x1 here, x1 minus 0x2. So I'm not writing 0x2 here, 0x2, I'm not writing 0x2 here, and minus 4x3, so I'm writing 4x3, and minus 28x4, so I'm writing minus 28x4, and 37x5, and 13x6, and 13x6 will be is equal to 0. So it is equation number 1. Similarly, I can write the equation number 2 again, 0x1. So here it will be 0x1, so I'm writing 0x1, 0x1 plus 1x2, here will be 1x2, so I write 1x2, then minus 2x3, minus 2 here, minus 2x3, and 12x4, so I write 12x4, and 16x5, and 5x6, so I write 5x6 is equal to 0. This is equation number 2. So we see that there are 6 variables and 2 equations. So how we can solve this type of equations? So we will, first of all, we will represent these equations in the form of x1, x2. Let's we represent in the form of x1 and x2. So because of we have 2 equations, so we can write in the form of x1 and x2. So this is our equation number now 1 and equation number 2 dash. It is equation number 1 dash and equation number 2 dash. So now let us we assume the rest of the value x1, x2 are written here, and rest of the value, let's we assume that x3 will be is equal to r, x4 is equal to s, x5 is equal to t, and x6 is equal to u. Let us we assume like this. So put all these value in equation number 1 and equation number 1 dash and 2 dash. So when I put x3 is equal to r, so I can write x3 is equal to r, so I can write 4r like here, 4r like equation 1 dash, and 28s, and 37t, and minus 3u. The same, yani we assume that x3, x4, x5 like a rstu. So we put these values in equation number 1 dash. So now we will try to solve, because of there are so many solutions, so we will try to solve. So let's we take a common from each of them, so we can say that, so r we can write r plus s plus t plus u. So the nullity of a will be is equal to 4. So because of there are 4 unknowns are there, so that's we say that the nullity of a will be is equal to 4. So rstuv are the variables we can, because of when we put different values we get a different answers. So we can take any value rstuv. So that's why we take. So this is the long process from which we can solve the nullity. So now so we are telling you some of the easier way to find the nullity and rank. So before doing some next method, there is a theorem that is called a rank-nullity theorem. So before going to discuss a rank-nullity theorem, there is some basic things are there. It says that, you just read it. I will come in a minute. You just read it. So it says that if A is M cross N matrix, then the row space and the column space of have the same dimension. So the dimension of the row space and the column space of the matrix is called the rank of A, and it is denoted by rank of A. So now we are going to discuss a rank-nullity theorem that is called over here. It is written here. Maybe this is called the rank-nullity theorem, or we say that that is a dimension theorem. So with the help of this dimension theorem, we can solve that problem that we discussed earlier. That is, n is equal to rank of A plus nullity of A. So nullity of A will be equal to the number of free variables in the solution Ax is equal to 0. So we have the free variables RSTU. That's why our nullity will be 4, was a 4, and the rank will be the number of leading variables in the solution X is equal to 0. So the number of non-zero rows in the form of echelon form of A. So either this you can do it, either you can do it. Both are the same. There is no any change. So we see a question, and this question it says that let the column vectors of a matrix A is denoted by A1, A2, A3, A4, and A5. So these are the column spaces are given here. So the question is find the rank and nullity of A. So this is first question, and the second question is find the subset of the column vectors of A that form the basis for the column space A. And the third question is, if possible, write the third column of A as a linear combination of the first two columns. So there are three questions in this question. So first of all, we will solve question number A, that is find the rank and nullity of A. So what we will do to find the rank? What is our first step? We will do it. So tell me, what is our first step? Anyone tell what we will do first? Yes, Hassan, you are right. We will reduce it into the row echelon form. So with the help of a row operation, we will reduce this into the row echelon form. So this is when you are going to reduce the matrix B will be a row echelon form. So here we are going to write in place of A1, A2, we write B1, B2, B3, B4, B5. So it is the row echelon form. So now, what is the rank of the matrix? What is the rank of this matrix? So yes, the rank of this matrix will be 3. So there are two equations of the rank. Yes, you are right. Because of the rank definition, number of non-zero rows, here we have number of non-zero rows are 3. So we say that because of this is non-zero, this is non-zero, this is non-zero, so we have 3 non-zero rows. We say that the rank of this matrix is 0. Or the another definition of the rank will be whatever the number of leading ones are there. So we have, if we see that we have 3, here we have leading 1 element, and here if we move from left to right, we have leading 1 element in the second row. In the third row, if we are moving from left to right, we find the leading one at fourth column, and if we are moving from R4 from left to right, there is no leading element. So there are only three leading elements are there. So we see that we have the rank will be 3. And what is what is a column space? So column C1 dash will be no, there is no, maybe he write on the second question. So our main topic is in A part he asked what is the rank and what is the nullity. So rank of the A will be is equal to 3. Now the second question is what is the nullity. So we know by the rank nullity theorem we can write is by the rank nullity theorem, rank plus rank of A plus nullity of A will be is equal to n. This is by the rank nullity theorem. So what is n in this place? What is the number of n? So if we count 1, 2, 3, 4, 5. Yes, you are right. So we have n is equal to 5. So we can write rank of, in place of rank we can write 3, and in place of nullity we don't know what is nullity, and in place of number of columns n will be is equal to 5. So now n is equal to nullity will be is equal to 5 minus 3, that will be is equal to 5 minus 3, that will be is equal to 2. So that's the procedure to find the nullity. So rank is 3 and nullity will be 2. Now let's progress on the B part. So in the B part it says that find the subsets of a column vector of A that form a basis for the column space A. So what are the column space? What are the bases of the column space? So we see that if you I'm clearing page. So here we see that what are the column spaces are there. So we see that there are how many leading ones are there. So in row 1 we have a leading one, in row 1 we have a leading one, and in row 2 we have a leading one, and in row 3 we have a leading one, and their row 4 is a 0, so we are not considering row 4. So in row 1 we have a leading element at first place. In row 2 we have a leading element at second place, and in row 4 we have a leading element at fourth place. So we have a column, we have a C1 dash, we have a column that is C1 dash and C2 dash, yes you are right, C2 dash and C4 dash. So these are the columns. And what about the main columns corresponding to these? So the main column corresponding to these columns will be is equal to, that is C1, and C2 dash will be is equal to C2, that is A2, and C4 dash, that is B4, will be is equal to A4. So yani we have A1, A2, A4 are the column spaces. So we see in the next. So it says that we have a leading one at B1, B2, and B4 is the basis for column space B, and similarly A1, A2, A4 are the basis for the column space A, as we found in the previous, as I showed you in the previous slides. That will be A1, A2, and A4. If you see in the previous slides, that will be A1, A2, and A4 are the leading ones are there. So put the value of A1. So when you put the value of A1, that will be is equal to 1, 0, minus 2, 0. Similarly, put the value of A2, that is 0, minus 1, 1, minus 1, 3. And when you put the value of A4, you will find that is 1, 1, and minus 1, 0. So now it is completed. So now see the last question. If possible, write the third column of A as a linear combination of the first two columns. So we can write like this. So B3 will be is equal to, yes, so we can write B3 will be equal to minus 2B1 plus 3B2, that is A3 will be is equal to minus 2A1. Yes, you are right. So like this we can write in this form. So that's the end of today's lecture. There is nothing more. So if you have any query, then you can ask me. Okay, hopefully you understand all, how we can find the basis, how we can find the rank, how we can find the nullity. So hopefully you understand these concepts clearly. Okay. So okay, wait a minute. I'm going to take attendance. Just wait a minute.